I am going to show you an example of the multispectral coherence tool in a dataset from New Zealand. I am Jose Pedro Mora, a graduate student at the University of Oklahoma. The dataset that we are going to analyze is the TOMT 3D Merge. This is a survey from the Trestles, Maui, Tui, and Opunaki 3D survey, and this is located in the Taranaki Basin of the west coast of New Zealand North Island. This dataset is a zero-phase wavelet and it's an SEG reverse polarity. This is the frequency distribution and this is the location. We are going to analyze this small dataset. Here you can see a step-by-step process to create a multispectral coherence volume. Here we are going to open the Similarity 3D window. We are going to selecting the amplitude volume, then we are going to choose the inline dip volume in crossline dip volumes. Then we'll change the name. We are selecting all the products that we want to have, and then we are going to select the multispectral option. Here we are changing from the broadband to multispectral, and here you can select if you want an individual volume for each frequencies. Here we can change the window and we can change the parameters. Finally, you can execute the Similarity 3D tool. After that, you can visualize the results. Here we are open the RGB combination, we are selecting that, and then we are selecting for the red channel, we are selecting from 0 to 30 frequencies. The green channel, we are selecting the middle ones from 5 to 62, and in the blue channel we are selecting from 30 to 91. Finally, you can change the parameters, and then we are going to take a look to a time slice. We execute the tool, and then we are going to have the final result of our analysis. You can change to see an interpolation or maybe a video of in a loop sequence. Energy ratio similarity is one of the results from the multispectral coherence tool. Here you can see a channel with very clear features and limits. In the broadband result you don't see that. Faults are not continuous in the broadband result, but if you check the multispectral result you have a clear vision of that fault. Some features are removed too, so maybe noise or some undesired features can be removed too. In this slide we can see three different window frequencies. The higher frequencies have low coherence. We don't see clear features, so we don't see any faults at all. But if we are going to lower frequencies, for example here from 30 to 91, we can see some faults. Here in the image we can see some channels also, so we can see clear features in lower frequencies. Higher frequencies, and this window you can know coherence goes from 0 to 1. This is the higher window in this slide. From 30 to 91 you have less coherent areas in this result. In the lower frequency range you can have more coherence areas. Here you can see clear faults and you can see the channel limits. The same for the middle range from 5 to 62, and the same from the 30 to 91 range. All these three volumes are going to be the input for the RGB combination in the next slide. This is an RGB combination from the three previous volumes. So we can see here in colors, the darker colors can show us the low coherence features. So we can see clearly faults and we can see the limits of the channel. But we can see in colors, we can see some interesting features. For example, in the yellow color we can see that these colors are mostly inside the channel, and outside the channel we can see some colors, some greens of blue colors or some cyan colors. The darker ones are the very clear features, and the other colors can show us very subtle differences. Remember that interpretation of stratigraphic features on seismic data depends on their bandwidth. Here you can see yellow colors inside the channel. Yellow colors are related to high frequency window. This is the time 1.8. Here you can see different faults and the channel delineation. Remember, each color can be related to a difference in frequencies. Here you can see an animation for the multispectral coherence volumes. 3 different volumes, 3 different frequencies. Thank you.